In front of you, either the one from the textbook or the one that I gave you. And you may notice I have a fondness for nerd humor. So, okay. They only get worse. They only get worse. Okay. So, what we want to talk about is how atoms and electrons behave. So the first thing you're going to write down is atoms are made of protons. Stop. If you want to, instead of writing protons, if you want to, instead of writing the word neutrons, what was our symbol for neutrons? Who remembers? N with a little zero to remind us it has no charge. It looks like the word no. And if you want to, you can go E negative. And in fact, for the rest of this lesson, anytime you see me having typed the word protons or neutrons or electrons, feel free. In fact, I encourage you, use the abbreviations, and that way it's both nerdy, but it reinforces what the charges are. Every time you write P+, you're reminding yourself that protons are positive. Every time you write E negative, you're reminding yourself, Candace, that the electrons are negative. So it's worth doing. So atoms are made of protons, neutrons, and electrons. Remember, we said that the protons are the atomic number. So on your periodic table, oh, you know what? Let's shoot an element. I hit element number 56. Go find element number 56, please. Barium. What's its atomic number? How many protons does it have? What's its atomic number? How many protons does it have? No. How many protons does it have? No. Stop. Okay, I want the right answer. I don't want sarcastic answer. 56. By the way, what's the name of the element? Barium. What do you do when your pet dies? No. Telling you, they only get worse. Okay? Now, here's our bit of new knowledge. So we looked at element 56. What was its name? Barium. How many protons? 56. If it's neutral, how many electrons? 56. The atomic number tells you the number of protons and the number of electrons when it's neutral. Now that's a fancy way, Pierce, of saying if you have 56 protons and 56 electrons, if you have 56 positives and 56 negatives, what's your overall charge if you add up 56 positives and 56 negatives? Zero, the fancy word for which is neutral. Now, it turns out in nature, most atoms don't want to be neutral. Most atoms have a longing to exist in a certain state. Now, I'm saying that they want, atoms are dead, they don't want anything, but I'll pretend that they want it to help us understand how they behave, okay? So, I wrote down here, electrons in neutral atom, that's also the atomic number, but this changes when it becomes, and here is the word we're going to be flogging today, an ion. Underline the word ion, that's going to become hugely important. Did I include the word ion on the sheet? No, so fill in the blank and circle it or star. That's going to be probably our word of the rest of the chapter. Lindsay's nodding her head back there, absolutely. Neutrons. So if you want to find out how many neutrons there are, it's the rounded off atomic mass, take away the atomic number. It's the rounded off atomic mass minus the atomic number. And this is why I said, now if you're good at doing two-digit subtraction in your head, you don't need a calculator, but I have no problem if you bring a calculator for this. I have a huge problem if your phone is your calculator. That's not acceptable, because there's way too many free apps that'll do all this for you, which is nerdly cool, but you need to know this for the provincial next year, so I'm sticking it in now. What was our element that we looked at? Element number what? Okay, so if I go bring up element number 56, and I'm going to zoom in a little bit. Okay, so here's element 56. What's its atomic mass? 137.3. 137 if I round off. How many neutrons does it have? Whatever 137 take away 56 is. Which is what? Someone has the calculator. Good. Can I do this in my head? 137 take away 56. It's going to be 81, I think. Double check me. Okay? So a great question is for me to give you an element and say, tell me how many protons, how many electrons, how many neutrons. The neutrons, we have to do some math. The most common mistake, Kiana, kids say, oh, it's got 137 neutrons. No, that's not the number of neutrons. That tells us the number of neutrons. Why does that work, by the way? Remember I said electrons weighed almost nothing? What makes up most of the mass of an atom? Two particles. Which ones? No, not electrons. Electrons weigh almost nothing. What are the two particles? Protons and neutrons make up almost all the mass. Since that's the number of protons, if I subtract, whatever's left over should be how many neutrons, because protons and neutrons weigh almost the same. Not quite, but close enough to 3 decimal places that we don't care. Keep going. So you ready? We're going to fill in this chart together. I'm going to try doing, we're going to do the first 2 columns. Then I'm going to hit pause and let you try filling in on your own the second 2 columns. So you ready? The first element they gave me, carbon. Find it on your periodic table. I think it's near the middle, near one of the top rows. Okay? What? Sorry? Let's fill that in. Element number 6. What's its symbol? Capital C. By the way, what did you say its element number was? You know what? That's how many protons and electrons. I kind of tend to fill those in together. What's its mass number? 12.0. So we'll just round off. We'll go 12. How many neutrons does it have then? 12, take away 6. 6. So this one has the same number of neutrons as protons. That usually won't be the case. It will be near the top of the periodic table, but Lena, as soon as you get more complicated, you often have more neutrons than protons. Okay. What's the next one? Copper. What's its symbol? What you say when you sign off on a text message. CU. All right? Wouldn't what be down one? Oh, symbol. Thank you. What's its number? 29? Oh, you know what? As soon as I know its atomic number 29, what else do I know? 29 protons. 29 electrons. Now, I should point out, Kiana, this is only true when it's a neutral atom, and in fact, it won't be true later on. But the protons and the atomic number will always be the same. What's its mass?
64.
Okay, 63.5. Do I round that down to 63? Do I round that up to 60? Up. You have to round off properly. 64. How many neutrons, whatever 64 take away 29 is? 30. 35? 35, I think. Don't forget to carry the 1. So, neon and lithium, I'm going to freeze the screen. Try filling this in on your own. Then I'll unfreeze the screen, and let's see if we end up with the same thing. By the way, this is a great test question. I'll give you a chart and some different elements, and you fill this in. So I like this question. I like this question. I like this question. Pink sheet or your textbook one. I don't have these memorized. Okay. I can get that. What's its mass? Lithium, I know, is Li. What's its mass? 7. Take about 20 more seconds to try and fill in that column, and then I'll unfreeze the screen. Let's see if we end up with the same thing. Finished?
I knew where they were.
Getting better at this? So lithium, I got 3Li7334.
Yeah.
Is that right? And then for neon, I got 10Ne12. 20, 10, 10, 10?
Yeah.
Okay. So my rant about how much information there is on this periodic table, I hope you're starting to clue in, and absolutely bring this to your test. Use this on your homework. This is what you're allowed to have on your test. You'll probably end up memorizing a couple of the more common ones because you get lazy, you get tired of looking them up, but you don't have to. So I have probably the first 7 or 8 memorized because I just got tired of looking them up. Although I don't have beryllium because it hardly shows up, but certainly I know hydrogen, helium, lithium, carbon, oxygen, fluorine. Let's keep going. Now, we said that electrons are arranged in shells around the nucleus. And it turns out how they are arranged determines how they react with other atoms. Once you've written that down, I'm going to say, put your pencil down and look up. Okay? Here's my periodic. I'll bring that back in a second if you didn't get it. Here's my periodic table. Oh, fit width, Mr. Dueck. Okay, here's my periodic table. All the atoms in this row here have 2 electron shells. Psst, 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 look up. All the atoms in this row here have 3 electron shells. Look up, look up. All the atoms in this row here have, take a guess, how many electron shells? 4. And then this is 5 electron shells, and 6, and 7, although it goes a little haywire as you go further down. Oh, how many electron shells do hydrogen and helium have? Just 1. Not only that. Not only that. It turns out that, I'm going to pick beryllium. Beryllium has, watch, 2 electrons in its first shell and 2 electrons in its second shell. Jordan, watch up here. If I pick nitrogen, nitrogen has 2 electrons in its first shell and how many electrons in its second shell? 5. This is how we can draw pictures of atoms, what's going on. Oh, hey, let's pick a tough one. How about phosphorus? Phosphorus has 3 shells. The first shell has how many electrons? 2. The second shell has 8. And then the third shell would have 5. We're going to draw electrons as little dots, but we're going to start to draw models. I can't call them pictures because they're kind of inaccurate, but they work. Models of what we think atoms and electrons and the shells look like. And it's all on your periodic table. And Dan, it's counting. You just have to know how to count. You have to know how to read it. But all I'm asking you to do is count up by ones. It's doable. So back to our notes. Electrons are related to elements are related to each other in the same vertical column because they have similar properties. We saw the alkali metals a couple of days ago. I showed you the video of how they explode when you put them in water. Oh, and as you go further down the periodic table, they get more reactive. I think cesium, when they dropped it in, it blew up the container, right? The reason they have similar properties, and this is really what explains all of chemistry, is because their electrons are arranged in a similar way. How do we know that? Why are they arranged in a similar way? Put your pencils down, look up. Let's look at this first column right here. So, let's look at lithium. Lithium is in which row? Row number?
1.
Careful. This is row 1 here.
2.
Row 2. What column is it in?
1.
It has 1 electron in its outer shell. How many electrons does sodium have in its outer shell? Also just 1, because if you count over, it's got 1. How many electrons does potassium have in its outer shell? 1. How many electrons does rubidium have in its outer shell? 1. How many electrons does cesium have in its outer shell? This is why they have similar properties. It turns out each of them wants to get rid of one electron. It has one extra electron to spare, and the further down you go, the easier it is to get rid of it. Scandium, look up right here. What column is scandium in? Column number, family number? 3. Do you know how many electrons scandium has in its outer shell? Count with me. It's going to behave very similarly to yttrium. Why? You know how many electrons yttrium has in its outer shell? 3. It's going to behave very similarly to lanthanum. Do you know why? Because it's got 3 electrons in its outer shell. The pattern of the electrons, Kevin, is what makes these have similar chemical properties. They bond similarly with other elements. They have similar properties because their electrons, their outer shell electrons, are arranged in a similar way. Examples. All alkali metals, all of column 1, they have 1 electron in their outer shell. And it turns out all of the action, Aiden, when it comes to chemistry, occurs in the outer shell. The inner electrons are buried and not accessible. All chemical, well, okay, I'm generalizing. Most, certainly this year, all the chemical reactions, Lena, that you look at, it's all going to be based on, hey, how many electrons are there in the outer shell? How far over from the left side of the column are we? Or how close to the far right side of the column are we? All the noble gases, that's the orange ones on the poster back there. That's column number 18. The reason they don't react is they have full outer shells. They don't want to gain or lose electrons. And so it's very, 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 very nearly impossible, difficult to get them to react with other chemicals. Going to go about 10 more minutes and then we're going to pause. The electrons in the outer shell determine how the element will react. In fact, they're so important. Leah, we have a special name for them. We don't call them outer shell electrons. Here is the word, and I'm absolutely going to ask you this word on the test. We call them valence electrons. Valence electrons. In fact, we call the outer shell the valence shell. Valence is the fancy word for outer. And I wrote down here, valence electrons are very, 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 you know what? I should have said very, 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 I can keep going for a while, very important. Are you picking up on my hint, Kyle? These are important. It turns out, for basic chemistry, if you want to know, if you want to be able to, Kyle, predict ahead of time how chemicals will combine, really all you need to know is what the valence shell looks like. And how can you figure that out? Your periodic table, count over from the left. That tells you how many electrons are in the outer shell, the valence shell. Bohr was the first scientist to show that electrons exist in shells. And he developed models to show how the electrons were organized. I wrote down here, look at page 66 in your text. I actually cut it out and photocopied it here. Looks like this. So here's what he noticed. Okay? These are what we call Bohr models of atoms. They show you, Lena, how all the electrons work. If you're missing something, I'll come back and show it to you, but stay with me here. Hydrogen in this side has 1 electron. Helium has how many electrons? 2. And it turns out he also showed that electrons, as the shells get more than half full, pair up. In other words, if you drew the electron down there, technically that would be wrong. And he showed, Lena, that that first inner shell can only hold 2 electrons, then it's full. Then if you want to get more electrons, boom, an entire new shell is required. Right here. This shell can hold 1, 2, 3, 4, 5, 6, 7, 8 electrons. 8 electrons. And as you go up, you gain 1 more electron. So if you see, here's element number 6. What is element number 6? Carbon. Carbon has a total of 1, 2, 3, 4, 5, 6 electrons. 2 in the inner shell, 4 in the outer shell. Hey, keep going. Let's look at element number, phosphorus. So silicon. Silicon is right below carbon. Carbon has 1, 2, 3, 4 electrons in its outer shell. Silicon has 1, 2, 3, 4 electrons in its outer shell, but the inner shell, shell number 2, has been filled up with 8. These are what we call Bohr model atoms. It turns out, Lyndon, as you move along the periodic table horizontally, you're going to gain an electron every time you move over. As you move down a row, you gain a shell. Riley, that you'll have to memorize. But once you know that, then the periodic table, by counting, tells you exactly how to draw these. And I'm going to be asking you to draw these like crazy on your test. We're going to practice drawing them like crazy. These are Bohr model atoms. Pick your pencils up. So, as I wrote here, as you move across the periodic table, the number of E minuses, the number of electrons, increases by 1 each time. Kind of makes sense, goes up by 1. I can remember that. Could have gone up by a yucky number. No, goes up by 1. As you move down the periodic table, the number of shells increases by 1 each time you move down a row. What does that mean? Candace, it means I'm never going to ask you to draw element number 93. Too complicated. I will ask you to draw stuff probably in the top 3 rows. That's fair game. After that, the drawings become huge and forget it. But you could. You can handle it. So, how do we distribute the electrons? The first question you ask is, what row are we in? If I'm in row 3, I'm going to draw a small circle, shell 1, a bigger circle, shell 2, a bigger circle, shell 3. And your circles don't have to be perfect. I can't draw these very well. My circles are all squiggly and yucky, but you can tell what it's supposed to be. This tells you how many shells have electrons in them. And the inner shells will be full. The outer ones will have gaps. The outer ones will have gaps. Then you count over from the left. Start on the left and just start counting across in that final row. That tells you how many electrons to put in the outer shell. Oh, and the inner shells, just count the entire row above how many there are. That's how many go in the inner shell. Do I have one where we're going to draw one here? Oh, I wrote down here, some students choose to remember the 2-8-8-18 rule. The 2-8-8-18 rule. And then I wrote, can you see where this comes from? Look up. In row 1, I know hydrogen appears twice. Don't count it twice. In row 1, how many? In row 2, how many? In row 3, how many? In row 4, how many? That's the 2-8-8-18 rule. I'm not going to have you go anywhere past that. Like trying to draw this would be such a huge, rhodium, element 45, would be so huge and so many circles it takes up your whole page. Forget it. But I would have no problem, Hudson, saying, hey, draw oxygen. What would you draw? You would draw 2 inner electrons. First circle around the nucleus, and then on the second circle you would draw, count with me, Hudson. Count with me.
1, 2,
Count with me, ready?
1, 2, 3.
Hudson, ready? Count with me.
1, 2, 3, 4, 5, 6.
So, no. When I get to oxygen, I would stop 6 in the outer shell. Okay? Got the hair out of your eyes? Okay. So some students choose to memorize that. You can make a little note. Yep. Yep. I didn't do 3 and 4 yet? Steps 3 and 4? You guys have a steps 3 and 4?
Yeah.
And they didn't show up in my notes? Or are they coming later? Are they there? Okay, finishing. Yeah, I haven't got there yet, so we're going to pause here. That's okay. It's all good.